So our first chapter of study this year was measurement. It was our first sort of stepping stone into the world of chemistry. And although we may not think of measurement as being quote unquote chemistry, it was definitely needed to do what we did for the rest of the year. So what you need to know for measurement, if we think about some of the topics that we covered, we were introduced to units of measure, right? The metric system is what 95% of the globe uses, with the exceptions of obviously the US and a couple of other smaller countries, but the metric system uses things like meters, liters, grams, seconds, Celsius. The SI system is sort of branching off of the metric system. It uses metric units of measure, but the SI system stands for the International System of Measurements, and that is just used as a common language for all scientists to communicate in. So even though in the US we use the imperial system that may use, let's say, pounds for mass, if scientists are communicating in the US, they're going to use kilograms, because that way any scientist in the world will understand what is meant and what's trying to be communicated there. We looked at different prefixes that we can use in the metric system to change the scale or the size of the measurement. We really focused on these, so milli and centi and kilo were the ones you should be really familiar with in converting in and out of. The other ones, not going to hold you responsible for converting in and out of them, but you should be at least familiar with those prefixes in the way that they can change the scale of a measurement. We reviewed scientific notation briefly, so you should be familiar with putting numbers in and out of scientific notation just in case you have to calculate. And then the bulk of the chapter, what was really new to us, was significant figures. And significant figures is important because we looked at the fact that if we measure something, let's take this pencil here. Right now this ruler looks like it's measuring 7, so the length of the pencil is definitely above 7.5 centimeters, but less than 7.6. So we can say that the length of the pencil is 7.5 with certainty. But then the last digit, right, we can always measure or guess one place beyond. So we can guess maybe 7.51 or 7.52, or we can guess 7.59 if we really wanted to. The last digit in any measurement is the uncertain digit. And all of the certain digits that we know for sure, plus the uncertain one, are known as significant figures. And significant figures are not really so important if we're the ones making the measurement, because we can get a gauge for how precise the ruler is, or in this case, how precise the graduated cylinder is. But if we are just given numbers in a problem and we have to interpret something about the device with which they were measured, then significant figures are important. So we went over some rules for defining how many significant figures are in a number, and they're summarized by this image here. So captive zeros are significant. Those are zeros that are sandwiched in between non-zero numbers. Any non-zero numbers are significant as well. And then the only other zeros that would be significant are trailing zeros that are found after a non-zero number, but also after a decimal place. So these two zeros are only significant here because they fall after the decimal and after a non-zero. If, for example, we had 500, those two zeros are not significant, and the 5 is the only significant figure there. Now, so what, right? The bigger conceptual understanding with sig figs is if we take that number 500, the fact that it has one sig fig is telling me, remember, significant figures are the certain plus uncertain digits. That's telling me that that is the uncertain digit. That's telling me that someone estimated that something was 500, whether it's grams, meters, what have you. We're not sure of the unit here, but let's say it's meters. That the estimation or the guess took place at the hundreds place. We did some calculating with sig figs, and there's different rules. If we're adding and subtracting, then we are rounding to the least number of decimal places, as was in the measurement that we were calculating with. And then if we're multiplying and dividing, we are rounding to the least number of significant figures as the measurement had that we were using to calculate in the initial calculation. There's one other example I gave us on here with the graduated cylinder just to practice taking measurements. Remember, we can measure one place beyond, so we use the graduations. The smallest graduations here are 1 milliliter because we're measuring volume. Looks like the meniscus is in between 36 and 37, so we may estimate that this is 36.7 maybe milliliters. We then looked at density, and we took our ability to measure both mass and volume and significant figures, and looking at if we can measure mass of something using a balance and volume using a ruler or the method of water displacement that's summarized here, then we can take that mass and divide it by volume to get a quantity known as density. Density is really looking at how much matter is in a given amount of space for a substance. It's a characteristic property, so it's really good for identifying substances at a given temperature because each substance has a unique density value. The only other relationship that you should be familiar with between mass, volume, and density is taking, like I gave the two examples here, if I have two substances of equal masses as indicated by the number of particles in each box, then the object with a larger volume is going to have the lower density because that mass is dispersed over a larger space, where the object that is occupying a smaller space is going to have the higher density because the matter is more compact, which is, after all, what density is measuring. And the example on the right here, the objects that are at equal volumes, as indicated by the size of the square, the higher density substance is going to be the one that has more mass in that space than the one with least mass, right? And again, indicated by the number of particles there. We really wrapped up the chapter by looking at error. Obviously, there's error in any measurement. You know, you might have read this as 7.52 or 36.8 milliliters. So that uncertain digit, there's error because it can be read in a couple of different ways. We went over really briefly some types of error. Really, we focused on random versus systematic, right? A blunder is a type of error that is just a careless error caused by you. That's really just an accident that could have been avoided. So the example we gave here, like when going to weigh the beaker, the student accidentally tripped and spilled the solution. That would not be a good source of error to include in a lab report because that is a blunder that's on you. Random versus systematic, a random error is an uncontrollable error that's caused by fluctuation of some variable. That's where we get sort of the high and low. The error is equally distributed around the value. It's equally high and equally low. Where a systematic error is errors that are identifiable. They can be fixed. They cause lopsided data. So in a systematic error, my error is going to be shifted either constantly too low or constantly too high around the value that we should get. And I gave you some examples of different random and systematic errors that you can go through there. But really what we should be familiar with in terms of these errors is looking at, are the errors giving me data that's accurate, precise, or not accurate or not precise? And those terms, although we use them in everyday language to really mean the same thing, in science they don't, right? Accuracy has to do with how close a experimental value is to the quote-unquote true value, and precision has to do with, when taking repeated measurements, how close am I getting to the same value? So I know we used the dartboards in class. I thought the pin the tail on the donkey was a pretty good, fun example of the difference between precision and accuracy there, so you can review that. We went over lab safety and lab equipment, so I gave us some of the common lab equipment that we use throughout the year. You should be familiar with the lab equipment that we used throughout the year, how to recognize it, why you would use it, how to use it, and you can reference your note packet for the more specifics on that because we did take notes in the beginning of the year there. And then we ended this chapter with dimensional analysis. We looked at conversion factors as fractional relationships that relate one unit to another. And dimensional analysis is really just a really quick and efficient method for converting one unit to another. And I gave us an example here that you can walk through. The important thing here is to identify what measurement you are starting with the unit, and then thinking about the pathway that you're going to take with the conversion factors you have to get away from the unit you don't want anymore and move towards the unit that you do want to convert to. And in this case, we're converting 24 kilometers per minute to meters per second. So this first conversion factor is converting kilometers to meters, 1,000 meters per kilometer. And then the second one is converting minutes to seconds, because there's 60 seconds in 1 minute. Again, making sure that they're canceling. So if it's in the denominator, we need it in the numerator to cancel, and vice versa. And then we just want to be careful when calculating it and keeping track of what your final units are going to be. So that was a quick overview of the key topics that we learned in Chapter 1. So you should be ready to take your review quiz for Chapter 1.